Yeah, hello. What I'd like to show is the twin paradox, the way it's supposed to be done. So what I've done is I've written down some things on a dry erase board, and this is basically the the thought experiment as shown on Wikipedia under twin paradox under well under the example given. So what we have here is we have the twin paradox, and we have some things going on. In Wikipedia, they show that the distance traveled. So what we have is, let me start over. There was a traveler on a spaceship, and he's going to be traveling to the nearest star, which is 4 light years away. He's going to be traveling at 0.8 c, and so we derive the Earth time to be the t equals 2 times the distance divided by the velocity, which equals 10 years. So from Earth's time, the traveler, it's going to take 10 years to travel both to the star and back. So on the ship's clock, so this is what the earthbound observer observes of the ship's clock after it makes the round-trip journey. So what we have here is a formula. This blah, blah, blah equals, of course, the square root of 1 minus v squared over c squared. So the ship's clock, after making the round-trip journey, is times by this fraction. So this is the Lorentz transformation. So what we get is 0.6 times 10 equals 6 years. And this is time dilation. So from the earthbound observer, the rocket ship's clock undergoes time dilation. So its clock slows down. So from the earthbound observer, he observes the ship's rocket or the ship's clock to say 6 years. Okay, so now this is from the ship's observation, or the rocket ship. So the distance is, the total distance is 4 light years. So when the rocket ship travels at or close to the speed of light, what happens is the distance undergoes length contraction for the rocket ship. So for the rocket ship, it's this formula, blah, 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 distance equals, of course, we have the Lorentz transformation times the light years, which is 4 light years away, equals 2.4 light years. So for the rocket ship, the distance went to 2.4 years. That's why the time was shortened from 10 light years, or I'm sorry, 4 light years. Wait a minute. Okay, I'm sorry. The distance one way is only 4 light years. So both ways is 8 years. So it shrank from 8 light years, or 8 years, it shrank to 6 years because the length shortened. So therefore the time shortens. So on Wikipedia, it has this chart. At the end of the experiment, it shows this chart. And what this chart shows, well, see, let me explain this. Wikipedia got this wrong. And I think every textbook I read and every video I read or watch gets this wrong. So they usually tell it from one person's, usually the Earthbound's observation or frame of reference. They don't give you the spaceship's frame of reference. And I'll tell you why that's wrong. That's incorrect. So if you look at the Wikipedia and look at this chart, it shows you an event, and it gives you the outgoing trip and the round trip. Of course, this is event in Earth years. According to the Earth, so this is all from the Earth's reference frame. This is the chart from the Earth's reference frame. So this is telling you the distance or the years that it took the space the rocket ship to go to the nearest star and come back. So what we find on the outbound trip, of course, this has all been done up here. In Earth years, it took 5 years to go out to the star. For the round trip, it took 10 years. Okay. Now this is the spaceship's years, as shown on his clock. So from the Earthbound reference frame, we see that his clock ticked 3 years going to the star and 3 years coming back, which gives you a total of 6 years. Now the distance, of course, this is the Earth's distance. The Earth didn't move, so it has 0 distance and 0 round trip distance. So now we have the spaceship's distance, which is this is from the Earth's reference frame. Is the outbound trip is 4 light years, and the return trip is 8 light years. So this is all from the Earth's reference frame. So now if we go to the spaceship's reference frame, things change. And I'll show you exactly what happens. So from the spaceship's reference frame, we know what the spaceship observed on his clock and his distance. But what we don't show is what happens on the Earth's clock from his reference frame. So what we have here is from the spaceship's reference frame, the outgoing trip was 3 years, of course, took 3 years, and the round trip took 6 years because the length contracted. So the time is going to be reduced. The spaceship's years. Okay, well, I'm sorry. This is incorrect. This is what we look at the Earth's clock. Okay? From the spaceship's point of view, let me read this to you. In B's reference frame, he traveled a distance of 2.4 light years. Okay, so we didn't get the length contraction. Yeah, we got the length contraction 2.4. So in B's reference frame, he traveled a distance of 2.4 light years to the star plus 2.4 light years back to Earth. So he traveled 2.4 to and 2.4 back. Therefore, the Earth moved 2.4 light years away and 2.4 light years back. Okay? At a velocity, from the spaceship's reference frame, the Earth moved at a velocity of 0.8 c. This is measured from the spaceship's reference frame. So this is from B's reference frame. Therefore, the total elapsed time on A's clock from B's reference frame is this formula. Let's see here. Well, I'll show you the formula. It's that weird number, the A thing. The distance divided by velocity equals, so that's the formula. Distance divided by velocity. So what we have here is, on this one, the distance was 2.4 light years. That's how far Earth moved away from the spaceship. The Earth moved away from the spaceship at 0.8 c. So we should plug in the velocity is 2.4, and this c is no, that ain't right. I'm going to never mind this up here. So so what we have here is a little. So anyway, from D divided by V equals 2.4 divided by 0.8 c. The velocity is 0.8. Gives 3 years. Now, if you times that, that's the outgoing trip. The return trip is a total of 6 years. So from the spaceship's reference frame, we have here. We have 3 years outgoing, 6 years for the round trip. Now, the spaceship did 3 years outgoing and 3 years back, which gives a total of 6. So the Earth, this is all to the spaceship's reference frame. The distance the Earth traveled was 2.4 light years away. The total was 4.8 on the outgoing and the return. The spaceship's distance was 2.4 light years and 4.8. So what happened is in Wikipedia, they left this 10 years. They did not include this 3 and 6. So we have a difference here. So they, let's see here. This is very, very complicated. So it took me a little while to figure this all out. So from the Earth reference frame, the spaceship's clock should have read 3 and 6. The Earthbound's clock read 5 and 10. So the spaceship's reference frame, the clock said 3 and 6. So we have a paradox here. So the spaceship sees the Earthbound clock as moving different than the Earthbound's reference. Well, it is, but so anyway, that's the deal.